questions there you can try. Proof, quickly, I want to talk about. This will be a very whistle-stop tour of proof. Expression for an even number, algebraically, would be like 2n. That's how you algebraically make sure it's even. And an odd would be like 2n or 2x plus 1. So this kind of question, prove that the sum of the squares of two consecutive even numbers is always a multiple of 4. So we've got to break that down word by word. Sum means add. Squares means square them. Two consecutive even numbers means like 2n and a number 2 more than it. So it's a consecutive even number, 2n plus 2. And squared, you've got to remember, is like a sneaky double bracket. And then it shows it's always a multiple of 4. So whatever you get algebraically, show that 4 factorizes out. If 4 is a factor, it is a multiple of 4. Okay. Prove the product of any two odd numbers is always odd. This catches people out. A lot of people with this will choose 2n plus 1 and 2n plus 3. Now, it didn't say two consecutive odd numbers. It said any two. So if they're distinct, they're unrelated, they're any two odd numbers, the way to algebraically guarantee they're not linked is literally use a different letter. So I'm going to use 2n plus 1 and 2m plus 1. Both are odd, but both have no underlying connection. You double bracket expand it, and you get something that has two lots of this bit, plus a spare 1 on the end. So this result, by design, is also odd. I think that was a good one to look through. Here's another little proof. I'm going to just talk this one through, because I think this is slightly harder to some of the ones you might have seen before. So prove that when an odd integer, an odd whole number is squared, the result is always one more than a multiple of 8. So if we do 2n plus 1 times 2n plus 1, you double bracket expand it, you get 4n squared plus 4n plus 1. Now it says prove it's always one more than a multiple of 8. And we can quite hopefully obviously see that 4 factorizes out of this bit with a spare plus 1. But that doesn't prove straight away it's a multiple of 8. It shows it's one more than a multiple of 4. But if we do a tiny little bit more work algebraically, we can see that n squared plus n factorizes a bit more. N could come out. So it's actually 4 times n plus 1. Now, this shows that it's one more than a multiple of 4. But the other little sneaky thing going on here is that n and n plus 1 are consecutive numbers. So what that means is one of them must be odd and one of them must be even. So if there's an even number times by 4, that means there's a multiple of 8 in there. Because there's something that's divisible by 2 times by 4. That means 8 can go into it. So this further little step actually shows that it's one more than a multiple of 8. And I think this is where most people get to kind of okay and think, well, I can show it's one more than a multiple of 4. But you don't often see questions like this. That's why I thought it was a good one to look at, where there's also an even and an odd thing going on if you further factorize. So actually that's 4 times one of them is divisible by 2. So that means 8 is in there, and then as a factor, and it's one more than a multiple of 8. Okay, so sorry I'm going so quick on these, but I think that was a good one to flag. The key points for proof: if it's even, it's 2 times n or 2 times x. If it's odd, it's 2n plus 1. These are like little generic things. Consecutive means like all in a row. Distinct or different means use a different letter. Sum is a word that tells you you're adding. Product means multiply. Difference means subtract. And showing it's a multiple of is like trying to factorize that number out of the final expression. These are all for algebraic proof. And this type of proof is called deductive proof, where you use algebra rather than numbers. You don't ever use numbers to prove something really, because you can't infinitely do that. The only times where it's okay to use numbers, and when you're asked to disprove something, show a counterexample, you can just sub something in that doesn't work and go, here, look, it doesn't work. But you can't do that to formally do the proof for every case. So if you're proving, you use algebra. If you're disproving, you can use a number counterexample. Okay, so there's a kind of crib sheet about algebraic proof.